Hello, and welcome back to Old School Coding. I'm using the techniques of 1990-ish and C99 to construct a system for simulating microcomputers of the time. My initial simulation is aimed at simulating an 8080 system to quantized signal precision, which means I want to have all of the various signals that would be running around in the system outside the chips, get nice, accurate waveforms of them quantized to some clock. So far, we're doing really well on that. We have most of an 8080, enough of the 8080 to actually start thinking about running some code. We don't have interrupts yet. We don't have DMA yet. But at this point, it is enough to run quite a lot of code, including mass storage, as long as we use PIO rather than DMA to move the data. So with that in mind, I've started building some external utilities, for instance, to manipulate the storage for the block storage for the BDEV and to provide the head end of the serial devices, which if I turn it on, for example, this would be the simulated terminal that would talk to the SIO, which would be the CDEV quote-unquote device inside the system. Now, this isn't all hooked up. We don't actually have the block device end of the block device talking to the disk storage yet. And I was looking at doing that, and it's using some code that's in bdev format.c. UTL format.c. So there's some code here from bdev format.c that I need to bring into the simulation. And before, when I built other things, I just kind of copied code. But I think in this case, it is time to set up a library so we can start thinking about not replicating code between executables. At the time, in the era I am thinking of, the most common way to do a library would be what's called a static library. Essentially, it's an archive, like a tar file, called an AR file, AR for archive, that contains a whole bunch of objects, linkable objects. So when you compile something from .c, you get a .o file, which is machine code, but there's all sorts of metadata around it saying, we're exporting these symbols with these values, and we're importing that symbol. When you get the value of that symbol, put it in here. So these are relocatable, linkable objects, .os. So you get an archive, which has a bunch of them, and it has a table of contents in it that says, these symbols are defined by these .o files. When you link against that library, it says, okay, we're linking this program. We've got these objects in the program so far, and we have these symbols that are not yet resolved. So we'll look into the library and find the object module that defines it. So you can have a huge static library, and maybe I only pulled 2 or 3 .o files out of it. And that means that we're actually fairly efficient. The downside of dynamic libraries, DLLs or SOs, shared objects, depending on what side of what fence you're on, is when you use a shared object or a dynamic link library, the idea would be that the whole thing arrives in your address space as a unit. And you maybe do a little bit of minor relocation, but generally the idea is that you have shared pages of memory. So it's basically read-only chunks of memory that you share with everybody else that uses that library, and we're done. I am not sure how DLLs work in Windows these days, and frankly, I'm not really interested. I'm more interested in how they worked back in late 80s, early 90s, mid 90s in the Linux and in the Unix systems of the day. That's what I worked on. I am trying to write my simulator as if I was going to be running it on a old school Sun desktop running Sun OS 3, maybe Sun OS 4. So from the time point of view of the tools we're working with, Think of SunOS 4 as being the bleeding edge stuff that's coming in with the new virtual memory system, changes everything, and treating streams specially. Now, I have my own thoughts on some of this stuff, but the VM model, the virtual memory model from SunOS 4 was nice and clean and well thought out and orthogonal, and it unified some of the concepts inside the kernel that people don't normally think about. The key thing is that if we were using a shared object, I would have to settle on doing something that would be specific to a vendor. Whereas if I do a static library, that was the common model of the day. So we're going to do a static library here. And we're looking at edev format right here. So before I start populating it, let's think in terms of how you build a static library. Now, a lot of this is built into the default rules of make. Make is the old, one might say, ancient build tool that says, I want this thing to be up to date, and here are those things that are components. And if one of those things is nearer than this thing, run this set of commands to update it. And then you get a whole database of default rules. Like if I have foo.c and I want to make foo from it, then here's the list of commands to compile a C program. So there are default entries in there for building the library. We'll be using that. But we need to hook it up so that it works with the rest of our stuff. So a couple of things to think about here. First of all, where do we want to put the source code for the C files that will go into this library? There'll be multiple .c files that are going to be compiled and placed into this archive. So we're going to want to put a library source file. So what I'm going to do is I'm going to put a directory at the top called lib. Now, we need to have multiple libraries, and I'm thinking that the first library we're going to do is the library will be shared with external code. So share between the monolithic simulation that we're building now and these small programs that we're doing. So we'll have external. Actually, let's say simaxt. This is simulator external interfaces. And I'm going to do sim internal. This would be for code that is used inside this simulation. And as we go moving away from a monolithic simulation to, I'm going to simulate a system by writing a program that calls up just the components for that simulation and puts them together. So instead of having one big executable that contains all the simulation components, and then you run it for this device or that device or the other device, we write a main that just has the components it wants. So we end up with smaller sims. I'll put that in sim int. I think we're going to do the same thing with inc. So inside inc, we have sim internal and sim external. So when you are pulling in the interfaces for talking to things that are in the library, the headers will be tucked away inside a directory specific to the library. This is not the way the system stuff works, but it's not uncommon. The other way to organize this would be to have a simaxt and simint directory in lib, and then inside that, oh, let's do it that way. Let's do it that way. Yeah. Let's put everything in lib. So what I'll do is I'll make a self-contained source tree inside simint and inside simext that generates the .a file. And elsewhere, we'll just say, when is the right time to go down and rebuild in that tree. So the top level directory will not have the rules for doing the build, but it will have the rules for what goes on inside it. So inside SimExt, let's go in there. I need ink. So when I'm using this, I want to say something like include simext foo.h, which means the file needs to be in a subdirectory called simext. Yeah, I'm coding myself into a corner. I do, in fact, need to have this here. There's two ways of arranging for these directories to be populated. One is to have a completely self-contained library source area, contained project, if you will, that produces just this library. And its installation instructions are, once we have compiled and built and tested the library, as the final step, once everything is done, we copy all of our headers out to the header install. So inc/simext would be a destination install directory. And we would copy our library to a library directory that people can pick it up from with their -L. I think I'm going to stand that on its head for now. I will edit the header files here in inc simext. So we have come full circle back to what I originally typed in. Now, given that our header files are here in inc, it would not be unusual, since we are integrating the library into the project as a sub-project that isn't going to exist on its own. It's not going to have its own Git repos and so on. Let's just put it in source. There we go. Now, zero-length git ignore files, they will neither add nor subtract any rules from Git telling it which files to ignore or not to ignore. But the reason why I have them here is this assures these directories are not empty, because Git tracks files, not directories. If a directory has no files in it, then Git will not create that directory when you populate it. I want to have these directories there. So the canonical way to do that is a zero-length git ignore file. That also means that I could put additional things in this ignore. It says ignore these files in this directory. So for instance, I could say in simext, I want to ignore star.o in case somebody does a compile in this directory and leaves the .o's around. I don't want them magically appearing in Git the next time I do a git add. Could do that. Will do that if I ever see files appearing in my Git status that I don't like. So there's our two directories. If we're doing it this way, this means that I really need to hook this up to my main header file. Okay, so extdir. So extdir is going to be the sources for the extlib. Rather, it's the directory where we find those sources, which means that I need to add them in here. If I add them to csource, then these files will actually be compiled to .o's and linked into the main thing. So these need to be kind of separate. src. just like that. Now, we need to make sure that these C sources, these ext sources, don't flow into the list of objects that gets linked together in the main program. So, got to be a little careful. Going to I'm looking at this, I'm wondering, where did ASL more come from? Oh, right. These really do belong here. Never mind. I should learn not to second guess myself. srcb, this is the base names of the source files that get linked together into the monolithic simulation, so we don't want to mess with this. OBJs, also, they get linked into the main thing. Verify. Where did my linked line go? Here it is. So if something appears in OBJs, it's going to get linked. We need to do something a little bit different here. We need to make a parallel mechanism for the directory. We will, for the library, we'll end up needing to write this code for each library. And if we get enough libraries, I will work through the features of make that got added in the mid-90s that allow us to iterate through a list of libraries doing the right thing. And it's pretty crufty. I may not do it. It may be something that is just not worth the effort. ext obj is ext source change that pattern to there. Okay. libsim ext.a is the name of the library. ext lib, this is lib a, ext lib is going to be just libsim ext. So what you linked with is simext, and it puts the lib here. So if I say gcc-l foo, this will look for a file called libfoo.a. So I want to say -l extlib and have this come up. We are going to need a source file here really quick. Let's steal a file from here. Let's say support. Can I grab support? How useful is support going to be outside the monolithic sim? Well, it gets us fail and stub, format, tau. Tau is not useful outside the simulation. I am going to defer working on support until I decide whether I want to move tau out or not. Bum, bum, bum. Hex. Hex is a good one because hex just says I'm parsing a file, I'm doing things, I'm doing a callback. So we're going to move hex down. We're going to start by copying it. Oh, no, we need to rename it. Ooh. Okay, this is going to break our compile. I'm going to copy it under a slightly different name. So the library will have something in it called hex parse. It'll have all of the same stuff. It will replace hex once I get things going. This will mean that the compile won't break at this point. And once I see that we are actually compiling hex parse into the library and linking the library in, then we can worry about actually making things happen. So we now have a single file in there. The ext source is not empty. Ext objs is not empty. Ext lib has the library name, and lib a has the library archive name, which means that when we want to do this, ld libs, all libs needs to have our library. Like that. There's a subtle difference between assigning with equals and assigning with plus equals in make. Basically, colon equals does it only once. Plus equals adds to it, and just a plain equals does the substitution many different times. It comes in handy when the thing on the right is a big, long thing that make has to do a lot of work on, because it does it. The colon equal says do it once and set it now. The equal sign says do it everywhere I'm expanded. I like to use colon equals where I can. And actually, let's go ahead and make that difference. So what we're building up here is as we add libraries, we'll tack them on here. So the library names will go on extlib, and all lib a is going to get the actual .a files for dependencies. So all libs gets pulled in here, and wherever we link, we're going to do that. So now, look at compiler output. We have a problem. No rule to make target libsimaxt.a required by live coding. Well, first of all, we don't have libdir set up. Second thing is, all these directories are getting, it'd be nice if they were like in order. There. Just put them in order by their name rather than by their value. We still don't have the rules to build the library, which we are going to add down here somewhere. We've got all of the modified compile rules. This is going to be compiling from extsrc. These all go into the same thing. And this says all lib. So I believe there was a syntax where we would say lib foo.a depends on lib foo.a, foo.o, and bar.o, and so on. And it would do the right thing. So if that's true, I think I can just put in we need an extlib-o as well. Oh, extobj we have. extlib-a. I'm actually not sure how to hook up that stuff, so make -p. And my editor just went away. Okay. Well, goodness. This happens sometimes, especially under Windows. Sorry, it takes me a moment to get this set up. Wait. So I'm not sure why that window is being rendered. There we go. Apparently, when I brought the window back, OBS said, oh, let me set it to zoom in so it's the appropriate size. So libsim.ext, like that. What rules did that get me? So you know what? I'm going to do this the manual way. I never did like these parenthesized rules because that would take an existing archive and update something inside it. So So extlib A is going to depend on extobj. What I'm going to do is I'm going to completely recreate the archive. Make sure that the command line parameters for AR have not changed significantly. So by default, it wants to use R and V. So R is insert the files into the archive with replacement. And V says verbose. We are not going to do that. We are going to use different parameters because I am building a completely fresh archive. So I want to do a quick append because I'm building it new. I'm going to call randlib. Again, this is something that was required back then, is not required now. These days you can use AR with the S option to add the index to the archive. We are not going to do that. C is create the archive, so we're going to create it and quickly add files. EQ. Fancy, fancy. AR files originally weren't just for libraries. They were just a general way of archiving a bunch of files together. So instead of having a lot of little files, you had one big file that carried them all, and basically precursor to TAR, tape archive. I don't believe any of the rest of this is all interesting. So running AR with S on an archive is equivalent to running randlib on it. I'm not going to use this because I don't believe this was available in the early 90s. And let's not use V. We want to stay quiet. But I believe that's all we need to do with AR flags. Okay, so no rule to make target obj hexparse.o needed by libsemixt.a. Well, there's that rule right there, axt source sent.c. The source semixt hexparse.c is, oh, okay. So we have created our library here. There's labcmext.a, and for some reason my editor has decided that .a files get printed with strikeout type, probably because there's something you don't want to put in your Git repository. So let's make sure that they're in there like that, so we don't automatically put the .a's in the thing. So I delete the A file and we do a make. You indeed see that it's creating the library. The difference is somewhere in here we need to have a load library archive. We need a link flags that includes -L. Not AS though. What's the difference between LD libs and load libs? I need to refresh my memory on that. I need to know what it is currently. So the longer name, load libs, is deprecated. So let's not use it. Now cflags doesn't carry the LD information, but we do need LD flags. That. So now link.c will have that. We're not using link.c in all of these. We actually are using it properly here. But I also need to use link.c here. It's just the one, so I can say there. Let's take a look at what the compile is actually doing to us. So we compile each of the modules. We then do the link, and see we have the inc, lib. We do also see that we compiled hex parse here. So now if I were to clear out the contents of hex.c, so now we do that. And this again. So when we compile the text test, oh, that's right, that goes into the. So strategies for testing library code are a little different. What I would normally do would be to have an external test suite that linked the library and ran tests on it. So you might have a test program for hex, which would link with the library and would exercise the hex stuff. And that seems to have worked. Yes. So at this point, I am going to make some changes to cover up the, I don't have a direct, oh, fooled me for a moment. I've forgotten that I had a directory called hex for the .hex files. Durr. Okay, so lib gets libsim.ext. We get inc. Oh, we want to move our header files as well. I'm going to just do this all in one chunk. So in common, we had something in common called hex.h. We're going to move that to sim.ext. We no longer have hex.c here. And this guy is now called hex.c. And we now have errors all over the place because people are including this file from its old location. So keyboard macro, search for common hex.h. We're now in lib.ext. Next error. libsim.ext. Yeah. Okay, so that compiles. The other tweak, when we're indenting things, we also need to indent our new source files. So the reason why modern tools have so many assistances for doing all these things that I'm doing are just adding a library, adding a file to a library. So I'm going through a bunch of steps. Once you've done all these steps a number of times, you start thinking about automating them. And then you start building up bigger tools. CMake started to come into play in the late 90s. At least that's how I remember it. As people took all these standard ways of doing things and locked them down. The reason why I don't use CMake is while it made it easy to do things the way the CMake authors wanted to do them, it made it more difficult to do them in any other way. So you had to be following all of their rules for their mechanisms to make sense. Maybe it's gotten better since then. Maybe it hasn't. But like I said, we're still doing this in the early 90s methods, so we're still doing all these things manually. So my new source files are in here, ext.src. We want to fix C includes in ext source. And we want to indent ext source. Now, if I go to my source file, let's say I did something that caused this to be badly set up. Let's do something that messes with our indentation. Boom, all fixed. So indentation reformatting is all set up. I believe this automatically already has the ink stuff set up properly. sim.ext. If I go into hex.h here, let's say I mess with my indentation on these guys. Is it true? Hold on. You know what? I need to include that. There we go. Now, because hex_FN is a type, it's not going to indent it there. I think if I even indent it manually, it's going to say, no, 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 no. That's all right. I would rather have this one declaration not have this tabbed out to the appropriate space than have all of my uses of it have an extra blank after the star there because it didn't know this is a type. This is because indent is not as clever as doing something that's built into a compiler. For instance, Clang format, much better. But like I said, early 90s tools. Anyway, so we now have a library. So what else do we want to do in this library? We've moved in hex. Let's make it so that our actual UTL code makes use of it. Now, bdev format has its own copy of hex. I've got to set my windows back up the way I like them here. So instead of bdev format having its own copy of hex, what I want to do is I want to use hex.c. So I'm going to pound include simext/hex.h, like that. So these are the only things that are pulled. Oh, okay, so this does bring in common support.h. So this tells me that support needs to be in the library rather than in common. So we'll have to resolve that. Anyway, this provides hex parse, which we no longer have local. And I believe that's most of the rest of this. Okay, so warning, fin redefined comes from the thing. We're going to use uppercase byte because that's the data type. Byte and cstir, hex_fn, fgetB defined and not used. But it's static, never used. Hex digit value, hex start code. Those are all part of the hex formatter. So here we actually use fail. This means that I do need to move support into the library before I can go any further. Okay. So support.h goes into simext. Support.c. Go back here to make clean, amper make -k. So common support.h. Let's actually, because I've got multiple things going on here, I'm going to use grep to find the problems here. Git add dot. Make sure Git knows about all of our added files. So Git's telling us I have modified a bunch of things. I have renamed some things. That's good. I do git grep -n to give me the line numbers. F because I'm just going to give it a straight pattern. And we're looking for include common support.h. Now, if Git thinks its output is a terminal, it's going to put a whole bunch of codes in there to change colors. This is actually an Emacs buffer, which just speaks straight text. So I need to tell Git not to colorize it. So our Emacs macro is search for include. I did it again. Okay. Search for include common support.h. And wherever we find that, we're going to backspace across that and change that to sim.ext. And next error. Do them all. And yes, this means I don't actually have my editor environment set up as a IDE that provides me with a global search and replace across the project. Again, I have avoided trying to do things in my editor that are more modern than what I did back in '91. So it all compiles now. And it runs. How about that? So now we have this external library which contains support.c and hex.c, and these files don't exist anywhere else. Okay, and now I can go back up to UTL. So we're now using hex from sim.ext. Yay! And most of the rest of this is specific to BDev format. Some of it isn't. What isn't is this stuff from here down. I want to package this all up as one thing that says map drive. Make sure I've got that right. So pound include. Don't know what I'll need. Support code to mmap the storage for disk. Storage into memory. Now, what I want to end up with is something real simple. Extern byte star map drive. Now, this is the idea is what we're mapping here is memory representing the current contents of the drive, which means if we have a floppy disk put into a drive, what I'm going to do externally is place the data in the file. And when you change floppies, it's going to externally put different data in the file. Well, hey, kitten. Oop. I'm wondering, my current model is to have a single file which contains the contents of the drive, but it doesn't say anything about the geometry or the size. I mean, I get the size by looking at the size of the file. But I think what I'm going to do is I'm going to reserve some storage at the beginning of it to represent what the drive looks like. This is not, I repeat, not the partition table. When we get to the point where we are simulating systems that are large enough that have disk partition tables, that's going to be the data in the floppy. What I'm thinking of here is just a cross-check. So we can look at it, we could say, well, set up this file. I hate doing this. I really hate doing this. It's a major change to the way things work, and I'm not doing that right now. So we're just going to map the drive file in. And what I want to do is I want to package all of this stuff up together. So we have a CSTR of the drive itself. So it's whatever we're opening here. This is the actual drive file. I think what I'm going to do is drive base name. Now I could go even further and just say int drive like that. So here are the drive files that I have already set up using the format utility as it currently stands. So currently the support code that we're calling doesn't know the path. However, if I have a bunch of different programs that are all talking, they need to agree on what this path is. So I do need this to come in with a drive number. I need for it not to require anything else. What we'll hand back is the mapped area. How does the caller know how big the file was that I mapped in? The caller is going to want to know the size of this mofo. Yeah, I am going to need to encode something in the file itself. So, what information do I need here? What I'd like to store is bytes per sector, sectors per track, okay, or cylinder, sectors per cylinder, heads per cylinder, and cylinders per drive. Cylinder is the term you use for track when you've got multiple heads. So, by their nature, these files we are storing are byte-oriented. However, they are all being executed on a host that is not byte-oriented. So what I'm going to do is so at the beginning of the header, we're going to have some data that's metadata. So if somebody says, I want to get the first byte from the disk, they're not going to read the header. So we're going to give an offset from the start of the header to the start of the data. That's fine. And we're going to have a data length, which is how much data is actually stored on the data. We're going to have some more other stuff inside. Per sector. call these so if I do this, if I write the geometry like this precludes drives that have variable geometry. What I'm going to do is I'm just going to have data length there, byte data. I am not sure whether this was valid in C99 or not. Invalid use of structure with, yeah, you can't have an array of drive headers when one of them is a flexible array. So all we can do is have a P drive header. That's fine. And let's just call this a P drive, drive data. So cross-check, when we map in the file, I can verify that the data length I see stored in the file is the same thing, is proper based on the actual length of the file. It means that we need to reformat our drives with the proper data length. Now it's up to our caller to know how this maps into cylinders and heads and sectors and sector size and so on. So just putting a differently formatted floppy in the floppy drive isn't necessarily a great thing. Why is CStir that? Did I not do this? I really at some point should go through and update all of these, so all the type defs I define appear in Indent Pro. This is because Indent doesn't look at all of your sources. It's a very localized window thing. So this gives me a thing called map drive, which I think will be what I want to do. So what are the steps here? I need to open the file. I need to get the size or set the size. I need to provide a way for the caller to set the size of the drive. Oh, there's two very different operations here. There's the operation of open an existing drive, and there's the operation of create a new drive. Tell you what, map drive will be the opener, which will open it and say fail if it's not there. Now I could take that value, or I could have the same parameters as open. Int flags. Open takes a int flags, good. So what I will do is I will take the flag, so somebody could call map drive, they could say map drive read only. They could say map drive read write create, and we'll do the right thing. So if we can create the file and it doesn't exist, I will need to know what length to give it. So creation is very different Yeah, let's not do this. So you can map drive, which will fail if the drive does not exist. You can boot new drive, which will create it. If it already exists, it will make it into this thing. But new drive will always zero it out. So new drive will say, place a, you create a new drive of this stuff. So bdev format is probably going to use new drive. It may call map drive and see if there's an error. So in both cases, what we want to do is do an open. Yet, we're not there yet. This guy is not there. So pound include the open drive doesn't exist yet. Static int open drive, int flags. Okay, so if the user running this has a UMask set, it will apply it. So what I will do is I will say, by default, make this file readable and writable by everyone. And if the user has a UMask set to 640 or 750, which is what I often had, it will then trim off the bits that are appropriate when it creates it. Implicit declaration of open drive. So there's that. So now we need to include the stuff for open. You're beginning to see the motivation for the for throw, for example. So fn needs to be a buffer created from the appropriate thing, and then we need to free fn. I'm going to allow up to 16 drives at the moment. So if bdevdir is not set, what I'm going to assume is that we are running from the top of the tree. And there's a directory called bdev below us that exists, and we're going to return that. Oops, that's not what the error was. So line 51, we're returning null here. If we call this over and over and over and over again, we don't want to be leaking memory, but we don't want to try to push this into a fixed buffer. This is something that everybody knew. You were writing C code in the late 70s, early 80s. You understood that if you had a static buffer, you need to verify that everything could go into there. And if you had a potentially unbounded string coming in, like the bdev_dir name, you had to pull tricks to dynamically allocate enough memory to store that thing you're creating, and then you have to free it when you're done. So I'm looking at my automatic build loop, and it is not yet looking in the proper place to re-trigger when I just update a utility or a library code. I notify wait needs to be told to also look at these guys. Now, why I don't just say put one more in there in case I have too deep and dir. Let's see, rebuild on what conditions? ASL dir star.asm. Any header files change? That. Source files in the top or in the down. Tester. And I might have subdirectories in tester. No, I don't. So that caused my loop to be doing weird things. Didn't watch inc/star.h. Okay. So what I need to do is do the wildcard inside Emacs, inside make, not inside this. So ASLDir. This is just ASLs. This is just H source. This is pretty much what I had before. C source, sub source. That we'll have to build. Actually, I'll call this L source, library source. Tests and utilities, so T source, U source. I think I had U source. Yes, I did. And the loop is doing the right thing. So now if I touch map drive, I can see that it is not paying attention to it. There we go. Now it's working. Sorry, quick diversion as we build up our build infrastructure to handle the right thing. So the idea here is to provide a default. So we get our bdevdir. We only call getenv once, so repeated calls will just return whatever it returned the first time. It's an idempotent function. We check the drive number, returning -1 with arrow set to enval if it's bad. If the malloc fails, we assume somebody set errno appropriately. And once we have it open, we're done here with the FD. We got that returned. So what do we do after we open the device? Potentially new drive is going to resize it. Okay, so we need something called size drive that does the right thing. All these things where I've got a size, could be size_t. Just going to use unsigned. So now, static int size drive. We do here, this is return f truncate. So we need to have a S drive data This may not be valid. The variable length of data here may do the wrong thing for us, in which case implicit declaration of f truncate, well, that's better. At least it didn't complain about size of. Okay, so for size of, it should treat data as having length 0. So new drive will set the size. Map drive does not set the size. We will need to get our page size and round page so we can do the mmap. Start writing mmap first. We're going to map in whatever we have. We need to know whether to fail or not. I think that's going to be in the caller. So the caller is going to need to know the size map in. Means again, these two are actually fairly similar. Tell you what, I'm going to say if data length is passed in as a 0, we're opening an existing one. Yeah. Okay, so pass in is 0 for data length. If data length is non-zero, then the drive is initialized to contain blank media of that length. Otherwise, expect the drive to have media of at least that length. And fail if not. No, I better make it explicit what's going on here. Okay, we're going to need to know the page size so we can round things up. So if data length is 0, what I want to do is set the data length to the data length from the file. We don't have the file mapped in yet, so I'm going to take the length of the file. Let's see, fstat. Yes, I often did this. This allows me to put other code here like static size t at equals 0 if ret less than 0, if ret equals 0. Actually, so once we have a page size, we never need to call the system again. Yeah, useless, but okay, if we do that, then we have lost track of whether we were creating or not. Ah. So I didn't actually think through this before I started coding, so you're getting to see the whole thing, soup to nuts. So yeah, there's too much stuff that is not in common between map drive and new drive. So let's do new drive first. So data length is an unsigned value. Any value here is actually valid. Size drive to data length. We're going to end up with something weird unless we do things carefully. Unsigned file length. Let's actually just do an F truncate here. I don't need size drive. Okay. Same thing here. Oh, this does need to be int. We'll change all these unsigned to ints. Just because it's easier to declare, easier to do the math, and we'll check things. So this test of the page length, this can fail if we are in a system that doesn't actually use pages. I don't believe there are any modern systems where that's going to fail, but let's put the code in because that would be my habit. If we have a valid data length, then this is going to be a valid file length. Okay, FD, we truncate the file. I'm going to make absolutely sure it's really clear what we're doing here. And let's see here, we are void star VP is equal to the map in of this stuff. If we got back a -1, we're going to return no. Now this will leave FD open, so we're going to If we call close on FD, it's going to change error node. So I think in the error case, if we do return an error from here, we're going to leave FD open, and we're going to count on our caller. He calls new drive and it fails. Under what circumstances would we continue the simulation? I don't believe we would continue the simulation at that point. So why did I suddenly decide to use integers instead of unsigned? It was so I could return -1 for these values, or use -1 for these values to indicate an error. So much of this logic is going to be duplicated, and what I will do is, as I work on this, as I create map drive from new drive, I will bring the subroutines out. But what that means is I really should inline everything to begin with. Okay, so protection read. We haven't yet pulled in those headers. Okay, so there's the create. There's the new drive stuff. Now we need to do map drive, which is similar to this. Difference is new drive is not writing the data. It's merely setting the length and returning it. What I do need to do set up, since I'm creating a dd arrow data length equals data length, mem set dd arrow data 0. Go. If you call new drive, it's going to do all the stuff for you. So this brings up map drive. All of this goes away. We need something like strtoul, but we want it to return just an int. I don't want to use a to I because there's no way to return errors there. I think strtol is my way to go. So DRV, we're getting a drive number, whereas this is actually there we go. The DRV is now the drive number. New drive returns a pointer. MP is now dd arrow data. We don't need to worry about the contents of the data length and drive. That's something that's already set, and we don't care about it. We know what the size is here. Okay, there's bdev format adjusted to use the library routines for mapping in the drive. So now we need to do map drive, which is just like new drive, but is read-only. I don't know how much of this is going to change. So map drive doesn't have data length coming in. It does have page length coming in. It won't know file length for a while yet. Since the first thing we need to do is get the name and open up the file. Then we need to get the file length from the actual status of the model, which is in man fstat. There's a status buffer, and the file length is equal to SB arrow number of bytes in the file, which is in st underscore size. So if the file isn't big enough to be a media file, then invalid. That pages is file length, so we round it up. I'm not sure what happens if the file isn't big enough for this. File length needs to be a multiple of page size. Which means here when we do the truncate, we need to set it to map length. Okay. Go. Do not have truncate. We do mmap. We do bring that in. We don't clear it. We don't set it. We don't do anything with it. We're just going to return it. So question, is there enough commonality? Are there blocks that are sufficiently large to be useful and sufficiently small to be carved off and sufficiently numerous to be useful? What are the important things that need to be coordinated? I think opening, so this part of this right here needs to be in common. So I need to do a static int open drive int flags int terms. And we're going to start with this all the way down through there. Difference here is we're not opening it with create. I think we don't need to pass in the 666 because that's common. I think RTWR can be implied, so either creating or not. I want to encapsulate the mmap as well. We'll return null if there's an error. So if void star -1 goes VP, return null. In the new case, we had some code that put it. We didn't change the name here. But here, do the mmap drive. Okay, old habit of mine that I want to get back into is if you're checking for equality with null, to put the null on the left so you do not ever accidentally assign null into the variable. So equality checks constant on the left. Now, after we do the mmap call, we can close FD. In these cases, if the length is wrong, oh, I could have mmap drive return an error if the length is not appropriate. The problem is if our length is bad, we're not closing the file. If the fstat fails, we're not closing the file. Can I do more inside mmap drive? If I pass in a 0 for the length, we will set the length of the file size and return an error if it's not appropriately aligned. That allows us to properly close ourselves down here if DD is null. So in the map drive case, do that. Correct. Page length gets known by this guy. So what do I want to do for the other case? So I pass in data length here. Yeah, I can move all of this down into mmap drive. If we do specify a data length coming into mmap drive, we will f-truncate the file to be the appropriate length. I'm thinking okay. You pass in a file that's badly formatted, we may correct it. File length, map pages, and map length, truncate the file, and we do the mmap. If the file is of an inappropriate length, do we want to trim it or extend it? I'm thinking let's do this sanely. Okay, so we're going to get the file length here from the file. We're going to work out that. Then we're going to say if mmap length there. So if the file is a weird size, we're going to extend it so we can see the entire file in case somebody wrote a file that was shorter, which is actually viable. You might send a file in that's fairly small. This also means that if you map a drive which has a header that says I am a gigabyte, the entire file is very short. We're not going to get the entire gigabyte. Means that it's up to the caller if he knows the length he wants. Oh. We do need to read in from the file what the actual length is going to be. What if it's corrupted? Okay, leave that to our caller. No, we can't do that. Data length. So if our if our file contains a lie about the data size, what do we want it to do here? Well, we're getting back to doing way too much stuff here. All this so that our caller can get the FD closed. Okay, that makes sense. So map drive is not modifying the contents of the drive. It may, however, adjust the length of the file to get it to map in properly, which means we do this. When we get to here, we have to trust that we have a consistent thing in the drive, which means that, yes, if I have an existing file, I need to either assert that it's correct or correct it. So what happens if I mmap a drive? It's too short. I keep circling back to wanting to see what's going on here. I'm thinking mmap drive needs to do the formatting for the case of data length equals 0. Yep. So we're going to pull out the data length, the file length. I am going to add another assert here. If data length is greater than the biggest file to support. Okay, so if the file length is too big, I'll have FD open so I can do another size drive. That doesn't update mmap length. Oh, frick. I've got too much stuff going on here. No, I think I really just gonna need separate routines for create versus open. Okay. Plus, I actually lose some stuff here. Yeah, I actually have already blown it. I've already corrupted this to the point where it's not working. I should have committed when I had new drive, doing the right thing. I should have committed it. Let's fold it all back together again just for new drive. bdev, we open drive. Drive gets so after sanity check the drive number, sanity check the data length. Find the bdev dir once, format the name once, open it, refn. So what I'm going to do is I'm going to create new drive again. I'm going to commit to Git before I start on the other part of it. We open it. This is for creating a new one. Okay. Page length is something I'm going to need up at the top. And I can check that before anything else gets weird. So we can actually do these computations much earlier. And I'm going to revert to ancient habit, declaring the variables at the top and initializing them as necessary. Because otherwise these just get to be too wide on the screen. So sanity check, sanity check, sanity check. System page length. Computation. Find A or B dev dir. Let's do that earlier. Get all of these computations out of the way. Construct the name, open it, free the name. Do the mmap. Cast it back into the drive data pointer. Leave that replaces all of that. I'm just using E and val right now. So in theory, there is something I can run that will do the formatting. We have the bdev format built. Okay, so mt.sh that is doing it. So let's get here and let's say fmt. That's because we replaced this with 0, 1, 2, 3. Okay, so with no files existing, we created drive A of size 0. Added drive A with a new drive of drive, SZ. And this got us a bus error. So I should have been a little more proactive on this. I'm going to take out the asserts once we're done. So I'm going to need the FN to be retained. Percent D. Nope. It's not. Okay, so it rebuilt, but it rebuilt badly. Okay, so we got to there. And this gave us a bus error. I didn't set the size. That's better. So once I've set the size appropriately, it works again. So now I'm doing what I should have done before. Let's commit this to a temporary area in Git. Release the Kraken. I actually don't have. Bring up Git Kraken. Git Kraken isn't starting. Okay, well, we'll have to do this manually. There's a lot of files that got touched. So what have we got here? Touch make file. I added this. So the git commit is going to be create ext library. Is there anything important that I committed in here that is not part of creating this library? Let's document what we've. Trying to document the particular functions I'm moving into the library. Scanning for those. We also changed the format So change to bdev format. The API changes in bdev format are now first line parameter is drive number, not file name, and file contains a header block with data length. There's map drive. Oh, let's mark this as work in progress because this is not correct yet. Got it. We moved into new drive. So the only interface we had to the drive before now was just create a new one. So we'll document that we are creating new drive, and then later we'll document that we're adding open drive or map drive. That's good. Okay, we're going to save this off. So if I mess things up again, we can get back to right where we are now. So here's mapdrive.c. Make another thing of this called map drive. And again, do it step by step. Map drive will not take the data length. It will map in the file. It will, well, first of all, we need to assure that the file contains a header. I'm going to do is I'm going to read in the header to determine the data length, and then I'm going to assure that the length of the file is long enough for that data. If not, I will make it longer. So, don't have a data length yet. Do need a page length. Don't have any of that yet. We're going to open the file. Now we need to find out the length of the file. fstat takes a stat buffer. I don't think there's any cases where this should fail unless FD is not open. Ah, right. So what I'm going to do here is I will actually map in the first page of the file and look at the size, and then unmap it and map back in the size that it should be. So we'll use mmap length for the length of the file for now. Again, the asserts are going to go away. So I'll need to write the assert followed by the actual guard condition. I'm not sure I can do a struct. Yes, drive head data. I don't think I can do that. Going to need FM handy. For my error messages. No. Nope, let's not complicate our code. Currently, I can do this. Declare these variables in the order that they're used. Thank you. Okay, so what are we doing here when we're opening the file? I may be circling back to declaring the variables as they're used, so let's just do that. I know this is going to cause the lines to be longer. So, drive number, figure out what directory they're in, hit the page size, instruct the file name, open the file, release the file name. If the open failed, we're done. Try to stat it. If the stat failed, we're done. So we got something open that we couldn't stat. All these things where we have to close FD in the failure path, so everywhere from here down to here, these all need to be map drive FD. What is my output of all of this stuff? Down through close FD. Well, we know that we need the FD. What else are we going to need? We'll find out. Now, the fact that I'm using ints here, if we were on an old Sun, this would mean I'm limiting all this to 2 gig. How about we return a P drive data out of this? This is going to give you a whole bunch of things that are undefined, so we need to fill those in. Now, I know I could just simply read the data length. But let's keep it like this so that we can be insensitive to changes in the layout of the drive data header. The warning, invalid use of structure with flexible data array member. Okay, fine. That guy needs to know page length. Maybe somewhere else I don't need to know it. Redefinition of map length. Okay. That pulled out map drive FD so that map drive could close the FD properly. We still haven't looked at any commonality. Let's move back to our formatter here. What I'm going to do is after we format the drive, so how am I going to unmap it? Let's see, I map in a drive and I want to unmap the drive so I can map the drive somewhere else. Okay, that does not compile. Comparison of expressions of different signedness. Oh, right. I'm not putting a string on the end there. I don't need to use my. So what did we get for our trace here? C, reading data length. C, clearing bytes of data. That's good. You see read size is 4. Data length. There. So we got through new drive. Did we get into map drive at all? Yep, we did. We got into this. We're going to go all the way down here, map drive, and done. Now, this guy also has this problem where he needs to close FD appropriately, and he may not be. So I'm going to make something for him called new drive FD. Or map, let's see, this is map drive FD. Yeah, map old and map new. So this is going to be everything from after we get FD open until we can close FD here. Here's FD open. Go all the way down to where we can finally close it after the mmap returns. So he is going to need to know the data length. Start moving it in one at a time. Say p drive data dp equal to map new drive. Okay, so he wants to do the mmap truncate of map length. Hold on. Can that be moved in? Yes, it can be. That means mmap pages also moves in. I believe means page length moves in. Get the parameters set up. Oops, not page length, data length. Okay, so we are diving through the first one to create the drive, and then diving through the second one to map it back in. A new drive and map drive. What are the commonalities here? If we want to do an open drive, I want to put that in both of these guys. Let's move as much into that as we can. I suspect I'm going to need to have a create flag. After fn, fd, all going in here. React comes from our open drive call. So this guy now says, check the data length, try to open it, maybe it's going to fail. Map it, close the FD, maybe the map failed. Then we write the header and return. Map drive does the same open drive. After page length format if. Very similar. Yeah, if I have just warnings, it's going to re-indent after it gives the warnings. So returning void star from a function with return type int. Control returns from non-void function. There we go. Start peeling this back. Take the asserts out and leave just the test condition. And I think I like the idea of declaring my variables earlier so that we don't end up with things running under the right margin. I know this goes against currently accepted best practices. However, those practices were not consistently best practice back then, or they weren't consistently recognized as best practice back then. Remember, we were just getting over the original K&RC where you had to declare your variables at the top. Now, if we're doing that, let's do it consistently. Int fd and these guys. So I'm going to be the first to admit that my error mechanisms here are not going to be giving a whole lot of good information. The important thing is that they are actually guarding against the conditions and that we are releasing resources so we don't leak them. So we are closing the FD at the appropriate time, and we are freeing memory at the appropriate time. Now, map new drive and map old drive have some commonality. Let's see if I want to extract some of that. I think the only real commonality is the dancing down below with the mmap. How much of this is common? Got to compare that with that. Well, the mmap is going to be common. Here we always truncate. Here we maybe truncate. If I had this always correct our size, that would be a little extra bit of paranoia. Oh, but that couldn't happen if we were read-only. Are we admitting that we are ever going to read a disk read-only? We are not. Ooh. What if a disk has a write enable tab on it? So currently we don't allow that. So map drive. What if I have a mode here? So we'd also have to get it down to here. No, let's not worry about that. But let's put that in. Now, this is not going to work with read-only files. That would be kind of cool for read-only media. I'm wondering if maybe we'd want a header, we want something in the header that says whether we can write it or not. A write protect value. Why not? Let's have some fun with this. So what we'll do is we'll set write protect. And if write protect is on, we will simply map it read only. Also means we need to open the drive read only first, and then need to reopen it read write if it's not read only. Well, we can do the map. Yeah, okay. Map new drive. The format, we're going to format the drive writable. So prot into prot equals prot. Okay, so if that write protect is turned on in that image, then we will only map it read only. Bada boom. However, we are still going to be messing with the file. We've opened it read write. We are going to truncate it if necessary, because a read only image that's all zeros at the end, we still want to extend the file and have zeros. Now, if we f-truncate the file to be bigger, I'm not sure whether it... Okay, so to do is this. We need to memset to initialize the new bytes in to contain zeros. That's a good question. If we create a file and we have truncate to set its length, is the new storage automatically 0? To be truncated to a size of precisely length bytes larger, the data is lost. If the file was shorter, it is extended. If the extended part reads as null bytes. Okay. So if we extend the file here, then we do have zeros being added to the file. That's cool. We're going to create a new one. We're not deleting the file first. There could be a pre-existing file, so we still need to have our new drive do this and explicitly set things to 0. Because there may be data in the file that we opened that maybe already existed. So there's our new formatting output. Here's our new files. Go into hexel mode, we see that the first chunk of the file here has the length of the file in hex, which is in, so 03E900. 3E900. And apparently the file is significantly larger than that. Yeah, so that runs that out to the end of the page size in the current host, which is probably 4 kilobytes. So now when somebody asks, map it in, what they're going to get back is a pointer to one of these headers, which will have the length of data that's available, a write enable, followed by stuff. I think what I want to do is also reserve some stuff. So I'm going to start the data at some offset into the file. What I'll do, I'm not going to use data. Data length. What we're going to do is when we format the disk, I'm going to say what disk offset the data is at, and the length of it, and the write protect. So now it's going to have an error. I'm going to offset the data. I'm giving us 128 bytes of header at the beginning of the file. I could give us an entire host page size, but I'm not going to. So when we format it, this will allow us to read files that have different header sizes than what we want. But when we create it, we will write in this. So map new drive FD, I think, needs to know H size. I do that. Here we go. That gets offset set up when I'm formatting it. Open Drive is going to thing, new drive FD. It's the file length, does the right thing. Map old drive FD. Length, file length, data length, data offset. I probably should put data offset after them. I'm not going to start assuring forward compatibility quite yet. Oh, there's the other thing I need to do. I need an unmap. Drive, map drive, and free drive. I guess it's okay to do. What? Oh, probably didn't get to compiling that because it didn't have that available. So if we didn't have a valid page length, we couldn't have gotten here anyway. Buffer overflow detected. Oh no. Oh, what did I just change? Changed a whole lot of stuff. Okay, eyeball it. Warning, call to read check warning cleared. Read call with bigger length and size of destination buffer. Ah, there we go. Right. There's our buffer overflow. Right there. Nice warning. Never would have seen that. So I believe now we can do this. Well, S might be a pointer. Let's do that. There we go. Running my eyes over this one more time. All this reasonable. Mind you, I am styling this not by current standards. Remember that. And I wouldn't be peeling off all those braces these days. This looks a lot more like code that I would have generated in the early 90s. Carefully, getting our closes in, doing this. This guy can return, but when he returns, we need to close FD no matter what we do. We've got free drive. Let's now call it. And that worked. So we create the new drive, and we're going to complain if the drive creation failed. Otherwise, we're going to map it in and start doing stuff. And down end, because this is a subroutine, let's release it. There we go. So here's our offset, only 80. So did I write a 32-bit? Hold on. That's garbage left over from before. Let's start with fresh files. Here we go. So format isn't rewriting the header stuff. That's a bug. Let's do this. Here we go. So that's going to zero out everything out to the end. Be good if I captured that. Do is int file length. So the file itself may actually be slightly longer if it's not a multiple of page size, but nothing outside the map routines knows about the additional storage that's been mapped in. Be nice if my mmap files came up in hexel mode automatically, huh? Let's see. Sure whether I to do all these add to lists. Guess I've just got it all set so it does it automatically. Oops. Excel mode. Not a variable. I need to do this. There we go. These guys automatically come up in hexel mode. So here's our D drive. Offset is 00000080, and the size is 07F80080. So it's 007F80. There we go. And 8000 FF. So we got the last bit is on the last page down below. Fine. So what was our goal here? Our goal was to write a library and have some functions that were shared between utilities in the mainline code. Well, we're halfway there. We are sharing support. We are sharing hex. We now want to put map drive in the BDev. This is turning into a very long stream, but I think it's worth it. So here in our BDev area, currently, let's take a look at our header first. Is it a comma? Yes, it is. So we are going to need to know about map drive. We have all this stuff that's set up, but we do need to have drive data for each one of the drives we support. So currently, I believe nothing in here knows about the number of drives. There we go. Seek. It's linked, reset. This is all standard stuff. Read data and write data. Cursors. Oh, that's right. Read from nowhere gives us a 0. Write to nowhere discards the data. Right. This is all was all just left as completely dangling. We didn't set the storage or anything. Cursor is equal to cursor limit, then seek to seek CTX. And CTX is visualization of struct S drive data star star star. Too many stars. So we now have some drives which we need to initialize. At some point, somebody is going to start setting up our things. Set cursor and cursor lim. So seek is just a pointer tucked into the BDev area. So it's really the implementer of BDev that does this. That's right. All of this stuff with the actual doing something with map drive was in the caller of BDev. That's right. Because we don't have drives. Don't know about map drive here. So it's the person that initializes BDev that is going to be setting up a seek function that sets cursor and cursor limit. And this is because I want to be able to test this. So where we set seek, is there a function we have to set this? This is bdev set seek. Define it there, macro there, we define it there. Which means we're using the macro here. So it's not so much that BDev knows about map drive, it's that the system uses BDev to access a map drive. So here's the seek function. It says disk pointer. Oh goodness, disk pointer needs to work out where the storage is for track sector, yada, yada, yada. Currently, it's just got this disk data thing. So that's all hidden. It's not part of this guy. It's inside BCTX. Each disk, but got a number of disks here. Inside this, got tracks and sectors. Data is going to be something we get back from a map drive. However, I'm going to keep it. I'm going to say B drive data. Do that. Okay. So now we've got this drive thing, which is not initialized and not used. Disk data. I'm thinking I'm not going to map the drive in until I need. Oh, no, that's bad. Disk init. We're going to get rid of disk data. I'm going to use disk init any. Disk init alone. Okay. Drive data is called drive. Now we should have compilation errors. So the data is at some offset. I'm thinking we really do want to have yeah, we do want data. I need to know which drive number. Disk init needs to know this drive number, not the name. Oh, it needs to know the name. Okay, let's run this. Test condition failed. Drive C has only 2 meg of the 8 meg desired capacity. That's because I actually want to have that configuration. Somebody's initializing it improperly. Who's calling disk init? Wrong size. There we go. 128 tracks of 128 sectors. This is maximum size 256 tracks of 255 sectors because sector 0 doesn't exist. And we are running. There's our halt. Shuts us down. And we see here that we are running at about 5x real time. More importantly, we actually opened up and mapped these in. So formatting, look here. I wanted to do a double density, double sided. So single density, single sided, double density, double sided. Oh, that's right. I couldn't find consistent numbers for how that was laid out. So I will have to just do that. In fact, I think what I'm going to do is this. There we go. Okay, so we've now formatted A and B as single-sided, single density, C and D as maximum size hard drives, back to our TTY and we say halt. And there we go. We are now supposedly reading and writing from our disks. Notice that if one of our disks is marked as read-only, we don't have permission to write it through mmap. But nothing in the device driver enforces that. And we have no way of reporting back an error. What will happen is the first time somebody tries to write a sector on a read-only, on a write-protected disk, it will crash the simulation because we are trying to store to a virtual page that's marked as not writable. And there's no way that the operating system, if the operating system doesn't seem to have a way to reference that. Now, what we could do is, where we set this seek up, go in here, the seek function calls into disk pointer. Data. It's actually during init when we do this. I'm going to toss on something at the end here. This says there. So we'll actually print something that it's write protected. Do we want to make that available in the next layer up? Oh, also, if we change media, we put a different floppy disk drive in, do we want to allow for a different formatting of the drive? For instance, if we boot on a single density disk and we shove a double density disk into the same drive, when we relog the disk, do we want to do the right thing? How would we make that happen? We would need to remap. It means unmapping the smaller drive, mapping in the larger drive. We need to know to remap. This is going to become a little weird. I think I'm not going to worry about it. Yep. So what we would really want to do with the write protect system is inside here, if we're write protected, then we would skip this. Or if we were write protected, we would point the cursor at a scratch buffer somewhere with a low limit. So we would write to a scratch buffer, but then it's the same cursor for reading and writing. Nope, can't use a scratch buffer because then we would need to copy our data. Guess we'll just have to handle getting Probably a bus error on this system. I'm not sure how it's reported these days. So at this point, I have not tested it, but I'm fairly sure that if we did some writes to bdev in the simulation, I'm pretty sure that it would actually show up here in our block device storage area. But the stream has been 4 hours now. I think it's time to cut it. I will consider what's going on from here on. Probably the next thing to do is start working on booting. I'm going to work on booting from our 4th executable here because a 4th actually provides us with some interactability. CPM, I do not actually have CPM disks yet. I do have some information. I've got a tar image of the files on the CPM disk, but what I really want is an actual bit-for-bit image of the actual disk. And that would be a little harder to do. After the first 2 tracks, the rest of it has to be laid out with the proper sector remapping. So yeah, we'll do 4th first. That's not for today. Wait, what is going on with Git Kraken? There it is. I saw it poke its little thingy up. Yeah, there we are. It may have been there all the time, just behind everything. So can I think? Let me see if I can get that up on the screen here real quick. Go capture. Here we go. Changes. We are going to amend SimExt library. Format. Okay. Boom. We're only using map drive in the simulation. Okay, boom. There we go. Push that. Again, documentation is lagging horribly. Anybody from back in the day will tell you that documentation lagging horribly is part of the normal development cycle. We're in the parts of the cycle now where we continue to develop without writing any documentation because we are fools. And with that, I think I'm going to call that a stream. Keep it small, keep it safe, and keep it fast.